In the last video, we have been discussing this conversation example, which calls itself recursively. One thing that is not particularly nice about this is that we are asking for a lot of input, but we're basically not really doing anything with it. So a more common scenario might be that we want to ask quite a number of questions, and potentially different questions, and we want to collect all the results. So we had abstracted from this ask function that asks a single question, but what I essentially want to do now is I want to write a function, askMany, that takes a list of questions, asks all of these questions and no more, and then creates an I/O action that ultimately gives us a list of strings as results again, but these strings that are the results should be the answers to the questions, basically the inputs that the user have given as a response to these questions. So that is a goal that we may have, and that is perhaps a slightly more realistic scenario than the one where we are just having localized conversation, but we're never doing anything with the results. We're immediately forgetting them again after reading them. Okay, we mentioned them in the output that was immediately following them, but there was nothing else that we did with the X being read here. So let's try to look what happens here. So we have a function here on strings, on a list of strings. So we can use our standard design pattern on lists. That's one of the options that we have. There are maybe other options, but let's perhaps first try that, right? So we basically introduce a name for the arguments. We have this problem to solve. We split into two cases. What if we have no questions, and what if we have one question followed by a rest of questions? Now, if there are no questions to ask, then we also know there will be no answer. So the list of answers should be empty in this case. Now you may be tempted to just write an empty list here, but that is type incorrect, because look, we've now written a list of something as the result type, but the result type is supposed to be an I/O action. So even though in this particular case we don't actually need to do any I/O, because we immediately know that there is a list that we want to return, namely the empty list, in the general case we will have to perform I/O, right? So we are saying this has an I/O list of string result type. So that means also in this base case we have to create something of the string. And now it again comes in very useful that we have introduced this return function that we can use in order to say, well, look, in this particular special case, we don't actually need to perform any side effects. I already know what the result is, namely the empty list, but I can lift that into the world of I/O actions. So that completes the empty case. But now in the QCons QS case, right, we still keep in mind we probably want to do a recursive call to askMany QS, but if we think about it, before, and now really before in terms of the effects, before we ask the rest of the questions, we have to ask Q. So there is sequencing coming into this, and I'm now just going to use do notation. And I want to ask the first question, and I can do that using ask or ask prime. I mean, they're equivalent, so I'm going to use the simpler name. And then that's an I/O string, not an I/O list of strings. So that's why this is currently type incorrect, right? So it says that the actual type of my expression here is I/O string, but what I'm expected to write is I/O list of string. But I can give a name to the result, for example, A, and now it's syntactically incorrect because the last statement on a do block cannot be having a left arrow and picking up a result. And now we can ask the rest of the questions after we've done this, and that is another I/O action. But we then want to combine the results somehow, so I'm just going to make this part of my do block as well. So I'm going to say askMany QS, and I'm going to call the result of this AS. And now I have the result A from the single question and the result AS, which is a list of strings from the recursive call. And now I can use return again to put the two things together. And now if I do askMany and I'm saying Q1, Q2, Q3, right, just to keep the questions apart. So then I'm being asked Q1, and then I can give my first answer. So let's just say A1 and A2 and A3, and I get the answers A1, A2, A3 as the result. And because GHCI always prints the final result, if I execute an I/O action within GHCI, I can see that this works as intended. A different option, just to highlight this as well, with the means that we already got, is to use lift A2 here, right? So that's yet again, like we keep writing multiple versions of functions. So you can recognize that what we're doing here is we're putting two things in sequence and then we're combining the results, right? But what we're doing, which two things we're doing in sequence, is already known up front. So we could just use lift A2, right, of askQ and askMany QS in this case. And then the operation that we do in order to combine the two results is just cons. And of course I need to rename this function. But this would also work. And it would be a little bit simpler, right? But there's more to this. If you look at this, so we started out relatively quickly saying, oh well, let's just use the standard design pattern. And it's nice that it worked, but we're basically for every string in the original list we're calling ask. So you could ask yourself, isn't this just map? I mean, your sort of higher order functions or pattern recognition sensor might say, well, this looks like a map, right? Because we're doing the same thing, calling the same function on every element of the original list. So let's see what happens if we just look at what is the type of map applied to ask. And we see that it takes a list of strings, so that is as expected. So we're operating on a list of strings, and then we're calling the ask function on every string, and we're getting a list back. So this is interesting, because map always gives us a list back. It doesn't give us an I/O back. But we're getting a list of I/O strings back. So a list of I/O actions. And that's a valid type as well, but it's a different type, right? A list of I/O actions is first and foremost a list. And within this list, we store possibly different I/O actions that each of them, when executed, would perform side effects and deliver a final result that has type string. Whereas an I/O action that returns a list of strings is different. That is first and foremost an I/O action that, when executed, performs side effects and ultimately results in a list of strings. Now, nevertheless, perhaps doing map ask is a valid intermediate step in a composition that we could use here, in a function composition. And perhaps we can go from a list of I/O actions to a single I/O action using a different function. And in fact, we can. And that function we're going to call sequence. And it is even more general in the sense that now we are not going to expect that we have a list of IO string actions, but we can just have a list of IOA actions. And we are going to turn that into a single IO action that returns a list of A. And it's called sequence because that is the decisive step, right? That we're choosing to take the original list and we're going to respect the order of the list and actually introducing sequencing between all the component actions that are defined by the list elements in the order as dictated by the list. So what we are making this sequence in which these IO actions that are contained in the list explicit. Previously it was kind of implicit, they were stored in the list, right? But now we're going to turn that into a single IO action by explicitly sequencing all these. And this is related in functionality to what we've been doing in askMany, right? So that's why it's not surprising that it will look somewhat similarly. So we again do pattern matching now here, right? And again, if we sequence just nothing, if we have no actions to sequence, then the resulting action will be a trivial IO action that does not perform any side effects, but returns the empty list as a result. So in that case, it is just like askMany is. And if we have multiple actions, we again use do. But now the difference is we don't have to call ask or something on the question in order to turn that question into an IO action. Now X already is of type IOA. And now we can just use X as the thing that we are going to run. And that will have a result of type A. So I'm going to call it A here. And then we can recursively call sequence on access, and that will have results as a list that are of type AS. And then we can put these two things together. I'm getting the error message here because sequence exists. So this is again a function that we are seeing in our course that is actually existing. So I should go up here and hide sequence from the prelude in order to get rid of the ambiguity on the call. And of course, this trick, if you like to call it that way, with using lift A2 here would work equally well to sequence. So we could have just said lift A2 cons X sequence access here as well. Here I'm just going to do it and not leave the original version there. Okay, so and now, right, if I look at the composition of sequence and map ask, the function composition, map ask goes from a list of string to a list of IO strings. Sequence then goes from a list of IO strings to an IO of a list of strings. So together, sequence and map ask have the right type for askMany. So that gives us yet another way of writing askMany that uses other functions. Now we did have to define sequence or recognize that sequence exists, so that's sort of a new ingredient. But as I've just shown, sequence exists in the prelude, and it is a more generally useful function that can be applied to other situations as well. So it is reusable on its own. So this gives you a way to reuse things in terms of in terms of functions that we essentially have already written or that we have already recognized. Okay. So that is a common pattern that, like, in the context of dealing with I/O actions, we can reuse variants of already known functions. So we cannot quite use map because map gives us a list and we want an I/O action again. So we still have to sequence after mapping. And a similar thing would happen if we are looking at filtering, for example, right? If we wanted to filter, but with a condition that that has a side effect, right? So, for example, if we want to write a filter function that that takes a list of file names and checks which of these file names exist, then we need a function that checks whether a file exists, and that will have type IO bool in the end, right? So then we need a filtering function of the form, let's call it filter prime for the time being, because it's not the original filtering, a to IO bool. And then we start with the list of A's, and then we have an I/O of a list of bools. Sorry, not an I/O of a list of A's again. Okay. And if we want to do this, right, then we can think, well, perhaps we can just start with filtering, right? If we have a predicate, perhaps we can just call filter on the list and the list. Perhaps we can just call filter p on the list. But now this is not quite working, right? This is not quite working because unlike in the situation with map, we here have a situation where the predicate is already returning an IO bool, and that is simply not going to work with the original filter. But we can still define this variant of filter using the knowledge of IO that we have so far. How can we do this? By using pattern matching again. So and how does this work? Well, in the empty list case, it's actually easy again. So there we don't have anything to filter. We just return the empty list. And there we don't need to introduce the p either. And here we now want to look at the result of p of x, right? But here we have to embed, and that's the reason why we couldn't use the original filter. We really have to embed the result of p of x into our sequence. We have to say exactly at which point we're going to run this effect. And so for this, we just introduce a do block again, and then I'm going to use an if, or perhaps we don't actually need to. Oh, so yes, we do. And I cannot immediately do if px, right? Because p of x is resulting in an IO bool. I cannot do an if then else condition on an IO bool. I first have to embed the p of x into my sequence of the IO action I'm building here. So I have to run p of x and give the result a name. So I can give the result a name b for Boolean. And then I can do an if on the b, right? Because p of x is of type IO bool, right? Because p is of type a to IO bool. b is now of type bool. Okay. And then I can say if b, then we are going to do one thing, and otherwise we're doing another thing. And perhaps the other thing is slightly simpler, because in the other case, I'm just going to call filter on p and on xs. Right? We drop the element x if it does not pass the test. But if x passes the test, then we want to keep it. And now again, you could think you can just write xcons, but we are in a situation now where we have to write or produce an IO action. We have to produce an IO of list of A's, and we still have something left to do. So, namely the recursive call, and then we want to change the result of the recursive call. So as a first approximation, we can use a nested do block here and make a recursive call to, let's call it ys, to filter, where we filter the remaining elements. And then after we have the result available of the filtered elements from the rest of the list, we return x cons ys. All right, so this would work. Now we really need to test this function. So we're going to do that in the next video. But before we test it, just one final word. We're going to simplify this slightly. So this is another common pattern that we see often, right? Just like we recognize the lift A2 thing. This is essentially the situation we are in if we just can do fmap, right? That's just a transcription of a call to fmap, because we are just making a call to filter and then we're modifying the result. So this is somewhat more easily written by writing instead fmap and then do a call of filter, pxs. And the function that we want to apply here is namely that we take the result of this and then prepend x to the result of this. But this is just a partial application of the cons operator, so it can actually be much more nicely written using just xcons as an operator section. And then perhaps it's even a little bit nicer to use the infix version of fmap, which is written like this, which I mentioned once before. Right, that's just a different name for fmap that we can always use when we otherwise can use fmap in infix form. So here we just make a call to filter. So now the two cases, or the two branches of the if then else, look more similar again. We do a recursive call to filter in both cases, and we prepend x in the successful case. But because we have to do that within the IO action, we have to use this fmap version here. Now this function, filterPrime, it also exists in the libraries. It exists in a module called control.monad in a more general form again. So we can briefly look at this. Control.monad filterM, it is called. And it actually has a class constraint based on the applicative class, which is a class that we're going to discuss in more detail later in this course. But if we consider M here to be IO, you can see that the type is exactly identical. So we can use it as the type that we have just been defining this filterPrime function at. A to M bool, so A to IO bool to list of A to IO list of A. So a better name for the function that we just defined would be filterM, based on that we generally want to try to use the names under which the functions are available in the libraries. Now, in order to actually test this function in a useful way, we need a useful IO action with a Boolean result. We can define one, I guess. We can define an IO action with a Boolean result ourselves. So let's say we could define something that reads a line from the input and then checks whether it has, like from the keyboard, and checks whether it has a particular property. So we could use the the ask function in order to generate something like that, a variant of our ask function. We could try to do this. So let's do string to io bool, ask bool, just for the sake of example. So we have our question, we ask our question, and then we get a reply, but then we just check. Oh, let's use do notation. We ask our question, we get an answer, and then we just check whether the answer is the empty. The answer is the empty string. So this is not, or perhaps let's call it ask null. It's not a very useful function the way it's written right now. So I'm just asked to type something, and if I type anything at all, right, then the result is false. If I type anything, if I type just the return immediately, then the result is true. So now I could use filterM with ask null on a bunch of questions. And now I'm going to be asked these questions in sequence. And if I hit return on the first, I type something in on the second, and I hit return on the third, then the test outcome was true for the first and the third. So only these two questions are returned. A more useful function to use in the position of filterM would be something like checking whether a particular file exists on the disk, for example, right? I mean, if we have a bunch of file names, we want to know which ones exist. But for this, we need to have a function that checks whether a file exists, and that requires a little excursion, which we'll handle in the next video.